This is video 22 in the series of reinforced concrete slabs. We have seen that to determine the yield lines that we can make use of the 30, 45 and 60 degree rules. But where is this rule coming from? Can we prove it? Just to demonstrate where this rule is coming from, we will take a corner slab with one side clamped and the other side simply supported. Then we have two yield lines, a yield line M with an angle alpha and a yield line beta M with a plastic bending moment beta M on the side of the fixed edge. Then the geometry is just A, the size is A of the slab. You can also make the same exercise with the size A and B, but it's in principle the same. And we have the distances S2 and S1. Now we make two assumptions. We assume that there is no interference of supports in the vicinity. So that means that the other supports further on have no influence on the angle alpha, giving the direction of the yield line. And we assume that the yield line pattern is correct, so that there are no other yield lines crossing around or yield lines in not straight lines or whatsoever. So those are the two assumptions. Yield line pattern is correct and there is no interference of supports in the vicinity. Then we take as a variable the tangents of the angle alpha, and we call it x, and x is of course then equal to S1 divided by S2, and A is S1 plus S2. Then the external energy E expended by loads moving is given by, because this is a triangle, so it means it's a total load of the triangle multiplied by the displacement divided by 3. Because the displacements delta, the maximum displacement, will in the equation disappear, then we can put this value as 1. It is the same, it's a scale factor in fact, so you can put it as 1. You can also calculate the external energy by taking the two triangles into account. Then you got this formula and you arrive at the same thing. It's Q8 squared over 6. The internal energy D dissipated by the rotation about the yield lines is given by, you have the plastic bending moment M projected vertically to the axis, which is S2, and over the angle delta divided by S1. So this is the first term. You can also project the bending moment M, plastic bending moment, vertically or perpendicular to the rotation axis here. Then you have S1, so it's M times S1 times theta, and theta is delta divided by S2, which is the second term. And of course we have also the yield line beta M projected on this axis of rotation, which gives you A. So it's beta A, and then multiplied by delta divided by S1. So this is D. Now A equals D, and then we can solve it for M. But first we will do some small exchanges. We divide in this equation A by S1, And then we see easily that A over S1 equals 1 plus 1 over X. We do that because we will create a problem in an unknown, which is the angle alpha, and we said that we will use X as the unknown. So now we can substitute the equations for X, or for A over S1, we will replace it by X. Then we have this expression. E is equal to D, and we rearrange the equation and get M, and M is QH squared over 6x divided by x squared plus beta x plus 1 plus beta. So beta is a degree of fixation of the line support, and x is the tangents of the angle alpha. Maximum bending moment for x, because now what we will do is this is the bending moment, and you have two parameters in it. We will optimize this. We will maximize this bending moment, because that's what we are interested in. We are interested in the maximum bending moment. So we take the first derivative and make it equal to 0, and this will be the case for x equal to the square root of 1 plus beta. Now just remember, when that's the tangents of the angle. When it's hinged, then beta is 0, because there is no hogging bending moment. That means that x is 1 or alpha is 45 degrees, which is in fact what we are using in the 30, 45, 60 degree rule. When it's hinged, it's 45 degrees. When it's hinged fixed, then beta is 2 for fixed, then x will be square root of 3, and then alpha is 60 degrees. So again, that coincides with the rule that we are using. You can now, this simple relationship, you can put it into a graph. This is beta m, and this is the angle alpha. Then you will see that alpha is, according to the value of beta, is coming from 45 degrees up till 60 degrees. When you have, for instance, another example, you have a balcony on 3 sides simply supported, then we see that if the value beta is bigger than 2, then you will have 2 yield lines like that. I call this lambda A, and I call this is the difference beta A times 2 times lambda A. And we will demonstrate here that you can look up the right position of the yield lines by maximizing the formula for the bending moment, just like we've done just before, the slides before. We will do now it for a balcony like this, but instead of the angle alpha, I will use lambda A, but that's the same. It's just another way of making it arithmetically. So the conditions, of course, is that lambda is smaller than 1 and beta is it's bigger than 2. Because if this is not the case, then you will remember that then the yield lines are not correct. So if beta is not bigger than 2, then you will have a situation like this. The extended energy E, external energy E is now equal to, we have 4 triangles, 4 of those small triangles, this, and this. 4 triangles. In each triangle, the surface is lambda A times A divided by 2 and multiplied by the delta over 3, because it's a triangle. And we have 1, 2, 3, 4 triangles. What is left is the rectangular. The total surface is beta minus 2 lambda times A and times A in the other direction, and total times delta divided by 2. And D is the bending moment M to projected to this axis of rotation, so it's m times a, and then the rotation angle is delta divided by the maximum distance, lambda a. And we got this at this and at this side, so there's 2, and then we have the yield line projected to the north to this axis of rotation, so it's again m times lambda a times delta divided by a, because now this is the maximum distance for the rotation around this axis. We have now, we can put E equals D and we get M out of it, and then if you simplify it, you got this formula. Again, we have 2 parameters, and we must remember lambda is smaller than 1 and beta is bigger than 2. We will now maximize this bending moment function according to alpha. And if you take the first derivative, you make it equal to 0, then you get this equation, and this equation is maximum if lambda equals this value. So lambda is a function of beta. So this is interesting to see. So the angle that the yield line is making is in fact dependent on the geometrical shape of the slab. It's dependent on the longest edge of the slab. When you use the 30, 45, 60 rule, then there is no dependence of the length of the edge. So you see that the 30, 45, 60% rule is an approximation. We substitute lambda in the equation, and you see that the maximum bending moment is a function of beta. Now, beta must be bigger than 2. And you can state that the angle is a function of a over b, but b is alpha, is beta a, and it is situated between, if you took the beta factor, then you can see that it is situated between 36 and 45 degrees. The less the influence of a nearby support edge, the more correct is the assumption of 45 degrees. You can put this in a graph. On the x-axis you have beta, which is this factor. So this is, for instance, 10 times, the length is 10 times the width in plan view. And this is lambda beta. And this is the same graph, but it's converted into an angle. It's just the angle of 34 to 44 degrees. So, and remember, lambda must always be smaller than 1 and beta bigger than 2. So you will see that the 45-degree rule is in fact only valid if this beta is very large. We can now rewrite the equation. This is the maximum bending moment for a certain value of lambda in function of beta. This is the general formula for in beta and lambda. It's not the maximum bending moment, but the bending moment for the 2 different parameters. Let's suppose that lambda is 1, which is 45 degrees. Then we see that the bending moment is equal to this formula. And there is a correction of the angle when beta, for instance, is 2, because everything depends on the value of beta. But if you take beta equals 2, then you have a correction of the angle. Instead of 35 degrees, it will be, instead of 45 degrees, it will be 36. And when you calculate now for lambda 1 and beta is 2, just one example, you can calculate the bending moment. When you do not make the correction and you use the 45, 30, 60 degree rule, then the maximum bending moment is q8 squared over 6. And when you use the correction for beta equals 2, then you will see it's Q8 squared over 5.55. So there is a small error when you use 45 degrees instead of 36. Now, why is the yield line of a one-way slab situated in the middle of the span? We said out of symmetry. Of course, it's out of symmetry, but there are other situations or cases that you do not exactly know where the yield line is. So how can we calculate where is the location of the yield line? Well, in this simple example, we will give you a method how to do so. When you take cross-section of it, this is a uniform. The slab is loaded with a uniform distributed load of Q. It's simply supported on two sides, and when there is a yield line somewhere, I don't know where, somewhere at a distance alpha L, there is a yield line, and there is a mechanism that is doing this with an angle theta. The other portion of the slab is 1 min alpha times L. Now we just do the math. We take the general formula for vertical work done. The external energy expended by the loads moving is equal to, we will use the short form, it's the total load, Q times B times L. That's a total load, that's the N, multiplied by the mean displacement, which is, because it's rectangular, delta over 2. And then the internal energy dissipated by rotation about the yield lines. It is on the left-hand side, it is M projected on the axis of rotation is B times delta divided over the maximum distance alpha L, that is theta. And then if we when we look at the right-hand side, then you have the yield line projected on the right-hand side situated rotation axis. It's M times B in the angle theta, which is delta divided by 1 min alpha L. E equals D, so you can get M out of it, and M is QL squared over 2, 1 min alpha times alpha. Now we have to maximize this bending moment, and doing so you take the first derivative to alpha, makes it equal to 0. You have an equation, and this equation says that alpha should be 1/2. So now you have proven that the yield line, which is in the middle of the slab, gives you the maximum bending moment. What is the location of the yield line of a one-way slab with one side fixed and the other side hinged? So one side is fixed and the other one is hinged. Where is the yield line? Now it's not so obvious anymore. There's no symmetry. You do not know. You do not know. It depends on the degree of fixation of this side. So we put the yield line somewhere in between. We also know, because this is fixed, that there is also a yield line for the hogging bending moment. This is for the sagging, this is for the hogging, and we call this beta M. This is the cross-section through it, and this is a mechanism, and the position of the yield line is alpha L from the right-hand side, measured from the right-hand side. Now we can again calculate the external energy, which is of course the same. It's just the total load times the mean deflection, and the internal energy dissipated by rotation about the yield lines. It is now the yield line on the left projected on the rotation axis. On the left is ML times B times theta, which is delta divided by alpha L. Then on the right, and then of course we also have the hogging bending moment of the hogging plastic bending moment, M times the projection on the axis of rotation times theta gives you this formula. We know now that the plastic moment on the fixed support is beta m, that's the degree of fixation, and E equals D, so we get m out of it, and then we have a formula m in function of alpha and beta. We will maximize this bending moment by taking the first derivative, and we obtain alpha in function, alpha is the location of the yield line, and alpha is exactly, the location alpha is a function of the degree of fixation beta. So this is a nice formula. We will just check it now. The maximum Hawking moment in function of the sagging moment. The Hawking bending moment is beta times the sagging bending moment. That if you, when you are using the equations of applied mechanics, then we know what the degree of fixation will be. And when you have simply supported, then it is QL squared over 8, or when you take the known formulas, then you know that the fixation bending moment is QL squared over 8, and the sagging bending moment is QL squared over times 9 times divided by 128. So this factor beta, which is the proportion between Hawking and sagging bending moment, is 1.78. This is from the mechanical, let's put it this way, mechanical input. So it's 1.8. Instead of 2, we used up till now the maximum degree of fixation is 2, but for this beam fixation hinged, it is the maximum fixation is 1.778. Then the location of the sagging bending moment for this degree of fixation, so we use this formula, will be 5 over 8, which is exactly what we find also in the known formulas. So these are the known formulas, and you will see that the location of the sagging bending moment is at 3h over L, but I have to switch it, so it's the other side, it's 5 over 8 L. So now you can have for this slab fixed, simply supported, for any degree of fixation, you can determine where is the location of the yield line or where is the location of the sagging bending moment, and the correlation is given by this formula. So if the beta is 0, when it's simply supported on both sides, when this is 0, then alpha is 0.5, which is correct, then it's in the middle of the span. And when you've got the maximum fixation, then it's 0.625, which is also correct. This was the general formula of the bending moment. You maximize it by choosing alpha equal to this formula. You substitute and you get the formula for the maximum bending moment of our problem. When it's hinged, beta is 0, and then m max will be QL squared over 8. This is the sagging bending moment, and this is the sagging bending moment. Remember, m is always the sagging bending moment, and beta m is the Hawking bending moment. So it's the sagging bending moment, and beta is 0. Then we find again QL squared over 8. When it's fixed, then it's beta 16 over 9, and then the maximum sagging bending moment is QL squared over 128 times 9. Looking at this formula of the maximum sagging bending moment, and we say if it's hinged beta is 0, if you put beta equal to 0, you get infinity. So how can this fit? How is this possible? Well, this is something for arithmetic. It's a limit, and I can prove it by saying that if you put parameter s equal to the square root of 1 plus beta, and you substitute it in this equation, then you have a maximum sagging bending moment equal to QL squared over 2 times S plus 1 squared. Just by making this substitute in this equation, you have this, and then you see easily when beta is 0, then S is 1, and when S is 1, you had QL squared over 8. But this is a nice formula for our problem, to solve our problem. Reinforcement now, we haven't told anything. When you are using yield lines, which is an upper bound method, what happens to the reinforcement? Well, in fact, it's not very safe to use this upper bound method because it gives you a maximum. It gives you a maximum in the sense of the maximum load capacity. And therefore, it has been proven in literature that if you add 10% to the value of reinforcement that you find in a normal way, then you are safe. You have a safe design. So it means that instead of using the bending moment that you have calculated divided by the yield strength of steel divided by the 0.9 times the effective depth, you just multiply this amount by 1.1 and you have a safe amount of provided reinforcement. You can also use this formula is exactly the same as this, but with FYD equals to 435 megapascal. So that means that this formula is very rapid to use, but the plastic bending moment is expressed in kilonewton meter per meter, and D is expressed in millimeter. So